Welcome back to this lecture on complexity in materials design, part 2, where I'll be dealing with the need to consider the design of materials as a multi-level design problem associated with decision support. So decision-making processes come to the fore in design and development of materials. To that end, we can consider extending the robust process control methods that Taguchi introduced some 30 years ago to the way we design materials to be robust against variation of design. So design variables for materials might include our target microstructures or structural elements at each level of hierarchy. For example, reinforcement phases, interfaces, grains, etc. And how those would vary according to typical processing or synthesis routes. And the idea is, rather than optimizing a single point optimization for target objective or objectives, to try to satisfy designs approximately while achieving relative insensitivity to the variation of those design parameters or design objectives. And we can consider that multiple objectives exist because we have multiple functions that are required. Take, for example, organic displays. They have to be durable, mechanically durable. They have to be flexible, constructed from multi-layers. They have to have high-performance electronic capability. Lightweight composite materials need to be conductive. They need to have electrostatic charge protection. Biomaterials and biodevices have to have mimicking of biological function while having appropriate structural properties, durability, and transport capabilities. So rarely do we consider a material for a single design objective. This is a complicating feature that leads to a basic problem statement of multi-objective optimization in terms of developing a potential family of solutions from which the user can express preference among this family. That candidate family of solutions is called the Pareto front, the Pareto frontier. This is expressed mathematically through minimization of an objective function subject to certain inequality constraints and equality constraints, and subject as well to certain elements of insensitivity to variation of design parameters. Now, in the process of pursuing this kind of systems design, we often make use of what are called meta models or reduced order models or surrogate models, and design of experiment strategies where we sample the space, whether experimentally or computationally, in what's considered an orthogonal and efficient way in order to derive information about the sensitivity of responses to the underlying structure or property characteristics. And so there are standard methods that you can read about that have to do with designing these kinds of methods of exploring the design space. And in the context of high throughput, we want to be able to do this fast. So we want to build on experimental and computational methods that allow us to screen candidate solutions in the early design stage, and we want to do it with design of experiment or orthogonal sampling methods. You can read about decision-making of materials under uncertainty in this book that was published some time ago, around 2009, by Elsevier, Integrated Design of Multi-Scale, Multifunctional Materials and Products, which has an extensive discussion of the philosophy behind extending engineering systems design to the realm of robust design of materials. So in summary, we've talked a bit about how materials discovery has historically been hit or miss, and the traditional design involves a number of serial steps and limited overall iteration. In the modern systems design approach, we embrace high throughput experiments, modeling and simulation in the early conceptual design stage or design exploration stage. And we emphasize design as a decision support activity or decision-making activity where robustness is a critical element to be able to mitigate uncertainty in the process of developing new and improved materials. Thank you.